Ladies and gentlemen, welcome to the second part of chapter 6, and here in the second part we are going to talk about continent collision. We see here a situation of a active Andean type continental margin underneath which an oceanic lithosphere is subducted, and eventually this process will lead to the closure of the oceanic basin and the entire subduction of the ocean that once separated two different continents. Once the oceanic basin is closed, subduction will come to an end, and accordingly also magmatic activity related to the subduction will die out. The two shelf margins, the former passive margin of the arriving continent, will then undergo deformation, and eventually this deformation will become very substantial. We might find here sediments that have accumulated over a very long time undergoing deformation and metamorphism, and the first stage might be uplift, which is essentially a response to elastic bending in the early stages of collision. If there are carbonate platforms, as we assume here in this example, the carbonate will be uplifted and will undergo chemical erosion, which might lead to features related to karst formation. The sediments that are forming in this early stage in such a region here might be turbidites if there is still seawater present. With increasing convergence and contraction, continent collision will form a thickened crust. And not only the crust is thickened, it's also the underlying lithosphere, and we form a high topography in a collisional mountain belt. On either side of these origins we might find fallen thrust belts, which we see here in the form of individual thrust slices on either side. Fallen basins can be related to the formation of these structures. The former passive margin might be buried deep and might undergo metamorphism, and the internal metamorphic zone will experience high pressure and high temperature metamorphism. Also, the former magmatic arc will undergo deformation, and the granites and gabbros will turn into gneisses and, depending on temperature, perhaps even into granulites. We see here a relic of the former subducted oceanic lithosphere. Such lithosphere will break off, and due to its higher density will start sinking into the asthenosphere and perhaps sinks as far as the core mantle boundary. Along the former boundary between the once separated continents, we might find relics of oceanic crust, and such relics of oceanic crust, for instance pillow basalts or parts of the sheeted dike or gabbro complexes in the oceanic crust, we call ophiolites. Ophiolites are important evidence for the presence of an ocean that once separated these two continents. Ophiolites are commonly found along the suture zone. The suture zone is a commonly irregularly shaped zone, often also not continuous, that marks the boundary between the two former continents. So after we have examined the principal architecture of a collisional origin in a cross-section, let's have a look at a plan view. Here we can see that the shape of continents and their movement path will control where and how origins are forming. And in this example here we see something that is very typical. In this region here, these two continents already have collided. Their movement paths towards each other have formed an Alpine style or Himalayan style origin. Subduction has come to an end, and we form here fallen thrust belts on either side. The suture zone might separate the boundary between material that belongs to continent B or continent A. but further south, due to the shape and the distribution of continental and oceanic lithosphere, we see that here still an Andean type plate margin exists. Here we still will see a subduction underneath continent B, and accordingly in the upper plate of this continent we will form a Andean type magmatic arc, perhaps with a fallen thrust belt in the back arc region. The collision in the northern part will slow down the movement vectors of continent A and continent B, and that can cause rotational plate movements as we see it indicated here by these two curving arrows. Eventually this oceanic basin also will close and the collision zone will propagate further south and overprint an active continental margin in the form of a collisional margin and the formation of a continuation of this orogenic belt that already has formed in the north. There are current examples that illustrate processes that we have just seen schematically. A good example are the Alps and the related mountain belts nearby. I don't want to examine the Alps in great detail because that would fill a long lecture series. I want to refer to the curving shape of the main alpine origin, which finds its continuation through the Balkans and to Turkey, and if you want, even to the Himalayas. But this curving shape of the alpine arc has its reason in a first collision of the Adriatic plate, which we see here, with the European mainland in that area. And this forced the Adriatic peninsula to rotate in an anti-clockwise sense. This rotation has produced the secondary contraction along the Balkans. The Dinaride mountain chain is a result of contraction of continental crust in response to this anti-clockwise movement of the Adriatic plate. This movement also caused a secondary subduction zone which starts in northern Italy and goes through the Adriatic Sea and Calabria and turns then west through Sicily. And where there is a subduction zone, very often there is a magmatic arc, and we find this magmatic arc all along the Apennine. The most prominent volcanic centers are obviously Mount Etna in Sicily and the Vesuvius in central Italy. West of this magmatic arc, in the back arc region, we find back arc extension, the Tyrrhenian Sea, which in fact is producing oceanic lithosphere, separating Italy mainland from Sardinia and Corsica, which we see on the opposite side of this back arc basin. The most prominent example of continent-continent collision are of course the Himalayas that have formed due to the collision of India about 10 million years ago, following the drift of the Indian continent across the Indian Ocean until eventually it collided and became part of the Eurasian plate. We see here the main structural features in East Asia, all of which are related to that continent-continent collision. We see prominent strike-slip zones here through Pakistan and also through Tibet and in central China, and here these large black arrows indicate a response of crustal mass movement to the northeast and to the southeast away from this collision zone, which has its main topographic features in the Himalayas and in the Tibet Plateau. In the recent history, these tectonic processes come along with very intense seismic activity, particularly here in Pakistan and northern Afghanistan. This large sinistral strike-slip zone is responsible for very significant earthquakes in the Himalayas itself, we find high seismic activity. And also here in central China, these large strike-slip faults are responsible for very significant and intense earthquakes related to the indentation of the Indian subcontinent into Central Asia. At the same time, we see that along other margins of the Indo-Australian plate, we still find subduction ongoing. Similar as we have seen 2 slides back, we see continent-continent collision here in the northern part, but oceanic subduction still underneath the Java and Sumatra arc, where we form an extensional back arc in the South China Sea and in the region here of Borneo. The large-scale lateral transfer of continental crust in response to the collision of a large secondary continent or terrain is called escape tectonics. We see here these movements of Southeast Asia to the southeast and to the east as a far-field response to the collision of India in Central Asia is facilitated by large-scale strike-slip faults like the Red River Fault that we see here, or the Altentag Fault that we see here running through Tibet, continuing for thousands of kilometers to the east. Escape tectonics have been simulated in analog experiments. Here we see a very simple one where a hard indenter in the form of a wooden block is pressed into a block of clay, and we see right from the beginning conjugated strike-slip faults are forming, which over time and with increasing indentation form a network of lateral strike-slip movements. And if we are leaving space on the eastern side of this clay block, the escape of material will move to the east. We see here a block escaping to the right hand side with increasing strain. A second major block is forming. This resembles quite accurately the situation in East Asia as a response of the Indian collision. We do not see escape tectonics to the west, simply because to the west there is the main part of the Eurasian continent, and movements cannot be easily compensated along subduction zones that we see here in the Western Pacific. Escape tectonics are a process that allow for large-scale lateral mass transfer in response to intense crustal shortening in the course of continent-continent collision. I want to show you a short video clip which is part of a much longer video made by Christopher Scottese, an animation of plate tectonics in the Phanerozoic. Here we are only considering the time frame in the last 66 million years, where we will see the movement of the Indian continent northwards and the collision, including the very intense topographic response to that collision and the escape tectonics in Southeast and Eastern Asia. So let's play this clip. We see here the time is counting. India is moving north. We see some topographic changes due to subduction, and now the collision takes place, and instantly we form a topographic high, which are today the Himalayas. We also see far field response in the entire Eastern Asian region, and we start escape tectonics here to the southeast. We see Japan drifting off, back arc basin is forming, and we see here the current continental shelf and shelf regions are developing over time. Let's play that again so that you can benefit from more detail. So collision takes first place in this region, followed then by propagation to the west. We see here high mountain belts are forming. We see at the same time also collisions further to the west. And we see the rotation here of Southeast Asia in response to that collision. We see here migrating shelves, changing sea levels. At that time, the high ground is glaciated. And for a short moment, we see the Pleistocene glaciation of the northern hemisphere. That was just here, this white flash. And that is the situation we find ourselves in today. I recommend that you visit this website. It's a beautiful video that shows not only the evolution in East Asia, but on both hemispheres for a time frame going back to the beginning of the Phanerozoic. Curie et al.'s textbook Global Tectonics from 2009 offers more detailed cross-sections of the successive accretion of terrains, not only for the last 66 million years as we have seen in the video clip. We are going back here to Permian Triassic time and the breakup of Gondwana and successive migration of terrains across what was then the Indian Ocean. That would have been the Tethys Ocean. The first drifting that takes place in Gondwana in Permo-Triassic time that is relevant to the formation of the Central Eurasian southern margin as we know it today is the drifting of the Lhasa Kyantung terrain that breaks off along a boundary that becomes the North Indian Shelf. The Lhasa Kyantung terrain drifts over the oceanic basin, separating Gondwana from Eurasia, and this one single block breaks apart into separate ones, the Lhasa and the Kyantung terrain, which are probably separated by a back arc basin that forms as a result of steep subduction underneath the Kyantung terrain. In the late Jurassic, the first collisions occur. Both of these smaller terrains collide with Eurasia and they overprint the Songpan-Gansi Triassic passive margin sediments which have formed along the margin of Eurasia. So here we see an example where a passive margin is overridden by an oncoming terrain, and we can see that the remnants of this back arc basin are preserved as ophiolites along the suture zone between the Lhasa and the Kyantung terrain. At that time, India has drifted off Gondwana, has separated from Madagascar and has started its drift across the oceanic basin, across the Tethys, and it leaves behind itself the Indian Ocean that we know today. Subduction is underneath the Lhasa terrain, and we would have seen in the Lhasa terrain an Andean-type plate margin at the time. In the late Cretaceous, the shortening and some uplift occurs in the context of the formation of this Andean-type margin, and eventually in the early Cenozoic, the collision between India and the Lhasa terrain reunites continental entities that had been separated for several hundred million years. This collision leads to an intense thickening of the crust along the margin between the traditional old Eurasia and India, and it involves the Lhasa, Kyantung and Songpan-Pansi terrains which already have formed an entity during earlier collisions. We see the older oceanic lithosphere still as a subduction zone underneath the Kyantung terrain and the Lhasa terrain, but this oceanic lithosphere will start to disintegrate and to sink as separate fragments downwards into the asthenospheric mantle. Here we see a more detailed cross-section through the Himalayas. We see from south to north the main Indian lithosphere with the crust and the lithospheric mantle. We see that the different terrains, the Lhasa terrain, the Kyantung terrain, and the Songpan Kansi terrain, the former shelf sediments of the traditional old Eurasia. They are separated by major suture zones that we see here in green color. We see that the main Himalayan mountain chain that we recognize as the Greater and the Lesser Himalayas are related to thrust tectonics. Southward thrusting occurs here in the context of the main Himalayan thrust that we see here. But of course, the pattern is much more complicated than what we see here on this simplified cross-section. We also see here that there is some continuation of the Indian lithosphere into the oceanic lithosphere of the former Tethys Ocean, which is bent downward and does not continue to depth because it already has disintegrated and broken off, and the oceanic lithosphere of the Tethys is now sinking as individual fragments through the asthenosphere and towards the core mantle boundary. One prominent feature of the Himalayas is the large Tibetan Plateau that we see here. That is the highest plateau on Earth. It's about 4,500 meters above sea level, and we see it here as a fairly flat and relatively featureless terrain that has dimensions of about 1,300 kilometers across and a width of about 500 kilometers. This is a very large topographic feature that at that scale is unique on Earth. Let's try to explain how it has formed. The Tibet Plateau is positioned in the area of the Kyantung and the Songpan Kansi terrain. We don't see it here on this non-exaggerated cross-section, but this is where we find the Tibet Plateau. And when we look underneath, we see that a part of the continental lithospheric mantle has separated from its upper continuation and from the crust under Tibet. The Moho boundary here indicates the crust mantle boundary. Some of the lithospheric mantle is still in place, but the majority of it has broken off and is sinking downwards into the asthenospheric mantle, as indicated by this dashed line that we see here. This downwards movement is called delamination of the lithospheric mantle. A consequence of this separation of the lithospheric mantle is the influx of hot asthenospheric mantle material into the areas that previously were occupied by the colder and more rigid lithospheric mantle. This causes an intense heat influx, and as soon as you heat up the lithosphere in that region, you will lower the density and you get a thermally supported uplift in that area. That is what is forming the Tibetan Plateau in this region. Here we see a more schematic sketch that illustrates the principle of lithospheric delamination that comes from van der Ploem and Marschak's textbook. We see here a strongly thickened lithosphere, a duplicated thickness of the crust and the lithospheric mantle, which creates this mantle root. This happens in the response to continent collision, and most collisional orogens will show such a mantle root. You need to remember that the lithospheric mantle is colder and denser than the underlying hotter and more plastic asthenosphere, and if you create such a large and heavy mantle root, it might come to a stage where parts of this mantle root simply break off because of the gravitational effect on this high density lower lithospheric mantle. This is illustrated here in this case. Here we see several disintegrated parts of this mantle root, and we see their replacement by hot asthenosphere that flows into that region and perhaps undergoes decompression melting or partial melting, creating the influx of magmas into the overlying, still thickened lithosphere. The loss of this heavy mantle root at the bottom of such an orogen would cause a very quick isostatic uplift that contributes to the formation of a plateau and a topographic high at the surface. So the delamination is simply the removal of a heavy and cold and high density part of the lithosphere, and that will trigger strong buoyancy, uplift and plateau formation. This was the last video in our second year level course in structural geology. Thank you very much for your attention.